Have you ever seen one of those topographical maps? You know, the ones with all the curvy lines. Those lines don't just tell you how high the ground is, they also show you how steep the hills are. Well, it turns out, in the world of electricity, we have something almost exactly like that. Today we're going to dive deep into the connection between the electric field and electric potential, and you're going to see how they're really just two sides of the same coin, two ways of mapping this invisible landscape of electrical energy. So that's the big puzzle we're tackling today. How do we connect the steepness of our electrical hill, which is all about force, to the height of that same hill, which is all about energy? In other words, how does the electric field, which pushes charges around, relate to the electric potential, which tells us how much energy those charges have? So here's our game plan. We'll start with a fundamental question, then we'll get a picture of what's going on by looking at a key diagram. From there, we'll build the actual bridge connecting the field and potential, see how it works with the real-world example, and then we'll wrap it all up with the most important takeaways and a quick summary of the formulas. Sound good? Let's jump in.
All right, let's properly introduce our two main players. First, we have the electric field, which we call E. You can think of the E field like the current in a river. It tells a charge which way to go and how strong that push is. Then we have electric potential, which we call V. This is more like the altitude of the river. It tells you how much potential energy a charge has just by being at that spot. So, how are they connected?
This right here gets to the absolute core of it. The electric field, E, is what we call a vector. That's just a fancy way of saying it has both a strength and a direction. It's like saying the wind is blowing 15 miles an hour east. But potential, V, is a scalar. It's just a number. A magnitude. It's like temperature. It just tells you it's 20 degrees right here. It doesn't have a direction. And that difference, it's a really big deal.
Okay, theory is one thing, but to really get this, we've got to see it. And this next diagram we're about to look at, it is the absolute key to unlocking this whole relationship. Let's break it down.
Okay, so take a look at this. What we've got are two surfaces, A and B, that are sitting inside an electric field. But these aren't just random surfaces. There's something special called equipotential surfaces, and understanding them is everything.
So what in the world is an equipotential surface? Well, let's go back to our map analogy. It's exactly like a contour line on that map. Every single point on one of those lines is at the exact same altitude. It's the same idea here. Every single point on an equipotential surface has the exact same electric potential, the same voltage. And that is a huge concept, because it means a charge can move anywhere it wants on that surface, and it takes zero work. It's like walking perfectly level along the side of a mountain.
Now, looking at our diagram again, you can see that surface A has a potential that we're just going to call V. The surface right next to it, B, has a slightly different potential. We'll call that one V plus a little bit of change, or delta V. Whenever you see that delta symbol, just think a small change in. So we've got two different altitudes, two different energy levels in our electrical landscape.
Now this is probably the most important rule of them all. Look closely at how those electric field lines, the E arrows, are crossing the surfaces. They always hit them at a perfect 90-degree angle. They're perpendicular. Why? Because the electric field always points in the direction of the steepest drop in potential, just like a ball will always roll down the steepest part of a hill. It's the path of fastest change.
Okay, one last little piece of the puzzle here. That distance labeled delta L. What's that? Well, that's just the shortest possible path between our two surfaces. It's that direct perpendicular hop a charge would make to get from surface B over to surface A.
All right. We have all of our pieces. We've got our surfaces, we've got the field, we've got the distance. Now we're going to use some basic physics about work and energy to build the mathematical bridge that connects them all together. So let's start with a concept you probably know: work. In physics, work is simply force multiplied by distance. In our little scenario, the force acting on a charge comes from the electric field, E, and the distance is that tiny hop, delta L. So the work it takes to move a charge from B to A, pushing against that field, is simply the magnitude of E times delta L.
But hang on, there's another way to define work. The work done on a charge is also equal to its change in potential energy. And that's just the difference in the electric potential between our two spots. So we take the potential at our destination, A, which is V, and we subtract the potential at our starting point, B, which is V plus delta V. A little bit of algebra, and what are we left with? Just negative delta V.
And right here, this is the aha moment. We just came up with two totally different ways to describe the exact same thing, the work done moving that charge. And if they both equal the work done, well, they must be equal to each other. So that means E times delta L has to be equal to the change in potential, delta V. We've connected them.
From here, all we have to do is a tiny bit of rearranging to solve for what we want, the electric field E. And there it is. The electric field E is equal to the change in potential, delta V, divided by the distance, delta L. And see that negative sign? That is super important. It's the mathematical proof of what we said earlier. The electric field always points downhill, in the direction of decreasing potential. This is it. This is the formula that connects the steepness of the hill to the height of the hill.
Okay, enough with the theory. Let's plug in some actual numbers and see how this plays out in a situation you might actually encounter.
Let's imagine we've got a potential difference of 5 volts. Maybe it's a battery. And let's say the distance over which that change happens is 10 centimeters, or, 0.1 meters. We just plug those values straight into our formula. E equals negative 5 volts divided by 0.1 meters. Do the math, and what do you get? An electric field of negative 50 volts per meter. It really is that straightforward. The number, 50, tells you the strength, and that minus sign tells you the direction.
So after all of that, what are the big ideas you really need to walk away with? Let's boil it all down to the essentials. Here are the two things you absolutely need to remember. First, the electric field always points downhill on our potential map. It's always going in the direction of the steepest, fastest drop in potential. And second, the strength, or the magnitude, of that electric field is the steepness of that hill. It's literally a measure of how quickly the potential is changing as you move through space.
And finally, just so you have it all in one place, here is a quick reference for the key formulas we put together today. This table pretty much says it all. That first equation, that's our bridge. It shows how the work done connects the field and the potential difference. And that second equation, that's the big result. It tells us that the electric field is what we call the negative potential gradient. In simple terms, the field is a direct measure of the steepness and direction of the change in potential. And that leaves us with one final thought to chew on. Based on everything we've just discussed, if the electric field in some region of space is 0, what does that tell you about the electric potential in that same region? Think back to our map. If the ground is perfectly flat, what does that mean about its altitude? Ponder that one for a bit. Thanks for joining me for this explainer.